Hi, and welcome to part 3 of Chapter 8, Reactions of Alcohols. Okay, so we have a few reactions that alcohols will do. And the first reaction I'd like to talk about is the one where it reacts with lithium metal, sodium metal, and potassium metal. Notice it'll react with any of these reactive metals to liberate hydrogen gas and form a metal alkoxide. What's happening here is that a sodium, for example, is actually losing an electron. It is being oxidized by the alcohol, and therefore the hydrogen that is produced is reduced to give us a hydrogen 2, which goes away as a gas. So this is a non-reversible reaction. Note this does not work with hydroxide. We cannot take ethanol and methanol with sodium hydroxide because it'll produce water. Water is just as strong an acid as the alcohol was. So the best way for us to make these alkoxides to act as nucleophiles is to use a metal to which we oxidize the metal and then reduce it down to hydrogen. The hydrogen goes away as hydrogen gas, and that gives us our material. Now that we have this anion for us, now we seeking out a positive charge, and it can react as a nucleophile in nucleophilic substitution reactions. It can also work as a base in beta elimination reactions. So we can use it to create ethers if we add it as a nucleophile, or we can use it to create alkenes if we use it as a base in an elimination reaction. So it's the first thing we can do is in water-soluble tertiary alcohols, this will react very fast with hydrogen chloride, HBr, HCl, and HI to produce their tertiary alkyl halide. Note that lower molecular weights, primary and secondary alcohols do not react under these conditions. That makes me think that we're probably going to end up going through a carbocation intermediate for this system. We can take water insoluble alcohols and bubble gaseous HCl through to convert it to that tertiary chloride. In fact, this system will also work with primary and secondary alcohols if we used highly concentrated HBr or HI to create their alkyl bromides and halides respectively. But notice this only works in where water is not present, such that the concentration of the acid is much higher than the concentration of the water produced. So let's talk about how that happens. And we said that maybe it goes through a carbocation. So our first step here would be to add a proton to the alcohol. Note that alcohol has those lone pairs that can accept a hydrogen. And so we first thing we do is acidify that alcohol to give us that oxonium cation. And then what this allows us to do is now, if we were attacked by a nucleophile or if we lost water, that would mean we would lose a neutral group. So we're losing a neutral group, so that's a good leaving group, as opposed to a hydroxide, which is one of our poor leaving groups. So the next thing that's going to happen is we actually break the bond between the oxonium ion and the organic substrate, giving us a tertiary carbocation. Remember, that's the most stable carbocation we can form, and therefore that makes it stable to be able to sit around and be attacked by a nucleophile. In this case, our halide acts as our nucleophile. It can come in and react with the carbocation to give us our final product, a tertiary alkyl halide. Now, if we want to do the reaction with that primary alcohol, we actually end up going through an SN2 mechanism because, again, primary and secondary carbocations are very poor compared to tertiary carbocations. But the first step in this is going to have to be also the protonation of the alcohol to give us our oxonium ion. Then, now that we have the water would be a good leaving group, we have to attack it with a nucleophile. So typically we use a high concentration of the HBr, in this case, or HI, such that it can act as a good nucleophile and displace our neutral water as our leaving group. Notice this is just a two-step reaction because it's an SN2 mechanism, and so it has to be bimolecular reaction. Okay. The other way to do this with primary halides in particular is to completely forego that waiting around for that alkyl halide the chloride ion to act as a nucleophile. We can actually create an intermediate where we have this sulfonyl chloride material SOCl3, which is thionyl chloride, it actually creates a reaction with the alcohol to create HCl plus a sulfur-based leaving group. So the oxygen actually from the alcohol leaves with the sulfur as the SO2. And that's where this makes it, the sulfur is reacting with it to make it a better leaving group. We're not having hydroxide leave as the leaving group. Okay, the other thing we can do besides displacing these alcohols is that we can actually dehydrate these alcohols, which means we're going to remove the OH from one carbon and then a hydrogen from an adjacent carbon, and that's what we call beta elimination. Remember, this is how we made some of the alkenes in one of the previous chapters. So for primary alcohols, we have to use very high heat and a very strong catalyst like sulfuric acid or phosphoric acid for this material. Secondaries actually undergo this dehydration at a little bit lower temperature. And if you think about it, we're starting to get closer and closer to carbocation instability. Tertiary alcohols actually require temperature at or only slightly above room temperature. So the ability to form that cation, helping the reaction move closer and closer to get those materials to go. So, for example, if we had ethanol, we'd have to heat it to over 180 degrees. Notice this is above the boiling point, so we probably need some kind of high pressure to make this reaction work, which would give us our ethylene gas plus water. If we go to a secondary alcohol like cyclohexanol, it reacts a little bit lower temperature and again gives us water plus our cyclohexene. But if we take our tertiary butyl alcohol, react it at room temperature with just a little bit of sulfuric acid, we can accomplish our beta elimination to give us our alkene available to us. Okay. We can also take into account the part of the dehydration of alcohols is that we will always, when possible, create the more substituted double bond. So if you think about it, when we talked about alkenes, the more substitutions a double bond had on it, so a primary, a terminal alkene was less stable than an internal alkene, which is less stable than a tri-substituted alkene, which is less stable than a four-time substituted alkene. This goes true, and we call this the Zaitsev rule. If you can rearrange to give either more substituted alkene, that will be your major product. Okay, and so the mechanism involved is just the same as if we were doing the other step of the reaction. It involves protonation of the alcohol first to give us our oxonium cation, which then can either leave to give us our carbocation, in this case a secondary carbocation plus neutral water, and then our water actually ends up being acting as the base. And so when our water acts as the base, the electrons from the hydrogen go to form our double bond with the carbocation, and the proton leaves with the hydronium ion. All right, so now that we can actually take an alcohol off an alkene to produce an alkene, we can actually take an alkene and add water across it. And we typically use this with an acid. We're using the alkene actually is now the nucleophile and reacts to form the alcohol. Again, we want to use large amounts of water. We'll form the alcohol. If we're pulling the water off, it'll form the alkene. And so we want to make sure that in these kind of systems, we use a lot of water with a little bit of acid catalyst to give us our hydration of our alkene, or adding water across our alkene. Okay, one of the other things that alcohols can do is that you can oxidize them. So right now we have a single bond between the carbon and the oxygen, and we can oxidize that down. So if we have a primary alcohol, we can oxidize that down to either an aldehyde or carboxylic acid. If we have a secondary alcohol, if we oxidize it, it'll only give a ketone. And if we have a tertiary alcohol, we can't oxidize that down. There's no hydrogen on a carbon next to it to be able to oxidize that. So the most common oxidizing reagents we use for that are called chromic acid oxidizers, or chromium-based oxidizers. In this case, we take something like an alcohol, we react it with chromium oxide plus some kind of acid and water catalyst, and that'll oxidize us down to the carboxylic acid shown here. We could also control the oxidative strength of the chromium by creating what we call the pyridinium chlorochromate, or PCC. When we do this, we actually lower the ability of the chromium to oxidize things, and we can actually take our primary alcohol and stop at just the aldehyde. We cannot do this with just straight chromic acid. The only way to do it is with this pyridinium chlorochromate salt, or the PCC. Again, note, all tertiary alcohols cannot be oxidized by any of these reactions, and are very resistant to that.